Hello and welcome back for part 4 of our look at the urinary system. During this video we will look at the processes of homeostasis as it relates to both reabsorption and secretion. So moving through the proximal convoluted tubules, moving through the loop of Henle, and moving through the distal convoluted tubules down into the collecting ducts. This might be a little bit of a lengthy presentation, but I don't want to break this up into two because all of this kind of flows together, no pun intended. So I'm going to try to keep this as concise as I can, but yet give you the detail that you need and not make it too overwhelming and too long as we move through this. So let's go ahead and get started. On this slide here, this is just some basic terminology that you need to be mindful of as we go through and look at the processes that are going to be occurring through the, again, proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. When we talk about tubular reabsorption, we are talking about the movement. Once again, we kind of touched on this in the last video, the movement from the filtrate inside of the tubule back into either the peritubule capillaries or the vasa recta down around the loop of Henle. And the way, and as that water is being reabsorbed from the lumen of the tubule into the capillary, that water can move either through what we call a transcellular route or a paracellular route. Transcellular means it's actually going through the cytoplasm and passing into the epithelia of the blood vessels. Paracellular means in between the cells. So going back to those fenestrated capillaries that are lining the capillaries themselves. And so water can also go into the capillaries in between those fenestrated spaces that we talked about in the last video. As that water is moving, whether it is transcellular or paracellular, there is something that is referred to as solvent drag. And I think this is a term that I have mentioned previously. Solvent drag is exactly what it sounds like. Things that are dissolved in water, water being the solvent, becomes dragged along for reabsorption. So if there are ions dissolved in the water, if there are molecules, if there are vitamins that are in the water, anything, whatever might be dissolved in that water, as that water moves from the lumen of the tubule into the capillary of the peritubule or the vasa recta, all of that's going to go with it as the water moves. So the water, being the solvent, drags with it whatever is dissolved in it. There are other ways in which we can transport material from the lumen into the capillary as well. And that's what those last three terms are that you see there. Symport is where you are transporting sodium and something else. And so something else is going to be attached to the sodium and it goes along for a ride. Antiport is where you are pumping sodium into the cell, and by into the cell we're talking about from the filtrate into the capillary, and at the same time we actually pump hydrogen out. And we'll talk about why that makes sense. Again, this is a topic that we've kind of visited when we looked at buffering systems in the blood, which we talked about in the respiratory system. This plays along those same lines as what was happening there. And then we've also talked about the SGLTs before as well, sodium glucose transport proteins. And this is where we're using glucose that is bound to sodium, and it's removed again from the filtrate and it goes back into the capillaries. In this case here, we're talking about the capillary tubule, the peritubule capillaries, because this is mainly happening within the proximal convoluted tubule. And so when we're looking at reabsorption, a lot of this is also enhanced or driven by the fact that you have large amounts of microvilli that are present along the surface of the tubules, more so within the proximal convoluted tubules as opposed to the distal. But the distal does still have some that are present. And so this diagram here shows and explains visually everything that we just talked about in the previous slide. And so the previous slide was the verbal, and this here is the visual. And so again, what you're seeing all right in here, this would be the transcellular transportation. Right, this is transcellular, everything that you see happening here. This here would be the lumen of the tubule. This here would be the cuboidal cell. This here would be the tissue fluid. And then this here would, of course, be the peritubule capillary, just as it is outlined for us. And so transcellular, again, is going from the lumen of the tubule into the capillary. This is paracellular. Right? This is paracellular because it's going in between the cells. Right? And notice that this is where that solvent drag is going to be occurring to. Pay close attention to this right here. All right. Water, urea, uric acid, sodium, potassium, chloride, magnesium, calcium, and inorganic phosphates, which we know is important in the formation of ATP. All of these substances can get caught up and transported through solvent drag. Solvent drag is less restrictive. In other words, more things get reabsorbed through solvent drag. Transcellular is a lot more selective because it's a balancing act of trying to maintain homeostasis inside of this cuboidal cell. And so what gets moved is a little bit more selective. And so understand that paracellular is less restrictive, and so you get a lot more things that are reabsorbed. Transcellular is more restrictive, and so you have a little bit more of a regulatory mechanism here. And so when we're looking at transcellular reabsorption, all right, let's kind of go through and look at all of the factors that are happening now within this area. So let's start with the sodium and hydrogen ion anti-transport. Right, so sodium gets reabsorbed, right, and this happens both in the distal and the proximal convoluted tubules, which is what we're more concerned with right now. And really, if we wanted to be a little bit more precise, we're really dealing with proximal convoluted tubules at this point in time. And so sodium very often gets reabsorbed in the proximal convoluted tubule. And as that happens, we're coming in from the, again, filtrate, and that sodium is collecting now inside of the cuboidal cell. Now, it doesn't stay there long, because as we move from the cuboidal cell into the peritubule capillary, we can see that we have sodium-potassium pumps that regulate that. We'll get to that here in a few minutes. So as sodium is coming from the filtrate into the cuboidal cell, we have to pump hydrogen ions out. And so hydrogen ions that are stored in the cuboidal cell gets pumped into the tubule fluid. Why? Homeostatic balance. If you just moved sodium in and that was it, you're supercharging, if you would, the intracellular or the intercellular environment of that cuboidal cell. You're making it too much positively charged, and that can throw off the balance of everything else. And so what we do is to maintain the electrical charge of the cell as we pump the sodium in. At the same time, we're removing hydrogen ions. And that, again, helps to maintain the balance of the charge. And by pumping the hydrogen ions out, you're also helping to regulate pH balance inside of the cell. So that is your antiport. All right. This happens without the use of cellular energy. Right? That is different than what is happening on this side as we move from the cuboidal cell into the peritubule capillary, where we have sodium-potassium pumps that are doing the same thing. But notice, as we pump that sodium now into the capillary, right, now we're getting rid of those positive charges, and so we have to balance that back out by bringing some potassium back in. This is energy intensive. Right? So this here is using energy, as does the completely lost my train of thought. The SGLT pumps as well, the sodium glucose transport pumps. They're also using, sorry, that's over here. This is also energy required as well. So that reabsorption of sodium is really what is driving everything that you see going on in here. All right. You also see some calcium chloride symports going on here. So if we are absorbing too many positive ions, we can actually then turn around and pump the potassium out. And as we do that, we're also going to be dragging some chloride ions out, which again helps to maintain the balance, because on the flip side, we have chloride ions that are being pumped in, and so we can sometimes get that collection of over-collection of negative charges. But because we have so much movement of sodium, we can afford to pump the potassium back out to again equalize the charge. Now, the transport of chloride ions, which is negatively charged, from the lumen of the tubule into the cell, and then from the cell into the capillary, is independent of, is not dependent of, the transportation of the sodium ions. And so that's why you see redundancy here within the movement of the potassium ions. We're both pumping potassium in to maintain a positive environment, but then if we get too much, we can pump that potassium out and drag the chloride ions with it as needed. And so they are two separate processes that are going on. All right. And so what we're really doing is we're creating an environment of osmotic and electrical balance. Osmotic from the perspective of balance of solutes that are in there. All right, so think of osmosis. All right, so we got to keep osmotic balance, because if we get too many positive ions or too many negative ions that are in there, you're going to throw the balance of water reabsorption off. So you have to keep that stable in order to keep the water moving in the right direction. And the flip side of that is the electrical gradients, because if you have an imbalance in the distribution of the ions, you throw off the electrical charge, which then can halt this entire system as well when we're talking about transcellular. So sodium concentration in the tubule fluid is about 140 what we refer to as molar equivalent per liter. That MEQ stands for molar equivalent. This MEQ right here stands for molar equivalent. All right. And then in the cytoplasm of the epithelial cells, of the cuboidal cells, that sodium concentration is about 12 molar equivalents per liter. So you can see that there is a dramatic drop there. The molar equivalent is defined as the amount of a substance which will either react with or supply 1 mole of hydrogen ions within an acid-base reaction. And so this is one way in which we can go ahead and regulate pH. And that's kind of what we were talking about with the sodium and hydrogen ion antiport. And so, again, the molar equivalent is defined as the amount of a substance which will either react with or supply 1 mole of hydrogen ions in an acid-base reaction, or will force the movement of sodium molecules into a cell, so that sodium doesn't build up due to sodium-potassium pumps. So you can again see what is happening on this side meets the first criteria for molar equivalent. All right. And then what is happening on this side meets the second criteria for molar equivalent. And so we try to balance out how much sodium is there to be able to maintain pH and to be able to maintain the concentration of sodium being diffused back into the peritubular capillaries. By the way, for those of you who have not had chemistry, what is a mole? A mole is not the furry thing that digs holes and tunnels into your ground. That's not what we're talking about here. Mole is the quantity of anything. Gummy bears, earthworms, sodium ions, whatever it is, that has the same number of particles found in 12 grams of carbon. And we define that as being 6.02 times 10 to the 23rd. Those of you that have had chemistry have heard of Avogadro's number. And that is what Avogadro's number is. So 6.02 times 10 to the 23rd molecules of sodium equals 1 mole. 6.02 times 10 to the 23rd sugar molecules equals 1 mole. All right, so everything is that constant back to 1 mole. So on a daily basis, you are actually filtering, producing about 180 liters of filtrate per day. That is happening within the glomerulus and the renal corpuscle, and that is through the tubules, through the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule, that is whittled down to about 1 to 2 liters a day of actual urine that is produced. Right? So 180 liters of filtrate produced per day, but that it only amounts to about 1 to 2 liters of urine that is actually excreted. And the reason for that is because about 99% of the water that is actually removed in the filtrate is going to be reabsorbed. And so reabsorption is key in the process. There's another video here for you to kind of review all of this with, and you have access to that in Canvas. And I encourage you to, if you want, stop this video, hop into Canvas and take a listen, all right, and kind of watch that, and then maybe come back in and finish this video. And so a little bit more on reabsorption. We got to talk a little bit more about pressure here and why reabsorption works. What we end up seeing happening here is, if you remember, in the renal corpuscle, more specifically in the glomerulus, blood hydrostatic pressure was equal to 60 millimeters of mercury, and that was maintained all through the glomerulus. Well, once you enter into the peritubule capillaries, that pressure now drops down to about 8 millimeters of mercury. So you've got low pressure in the capillaries. You've got low pressure within the capillaries. Now remember, all of these proteins have stayed in the capillary. The red blood cells have stayed in the peritubule capillaries. The white blood cells have stayed in the peritubule capillaries. Large, negatively charged molecules have stayed in the peritubule capillaries. So you end up with very low blood hydrostatic pressure, but you end up with extremely high colloid osmotic pressure. All right. Not to mention that you also have very high tubule hydrostatic pressure. In other words, you've got very high pressure in the proximal convoluted tubule, because that's where all of the fluid, that's where all the filtrate now is. So low blood hydrostatic pressure, high colloid osmotic pressure in the peritubule capillary, coupled with very high tubule hydrostatic pressure, drives reabsorption, because that water wants to go from an area of low solute concentration to an area of high solute concentration. That solute is your colloids. That's that suspended material that is left behind in the peritubule capillaries. And so that water is like, I've got all of this pressure that I'm exerting on this wall of this proximal convoluted tubule. There's not a whole lot of solute in here compared to what is over there in the peritubule capillary. And so that water is forced. It's driven from the filtrate back into that peritubule capillary, forcing reabsorption all along the proximal convoluted tubule. All right. So again, the factors that are contributing to reabsorption through the proximal convoluted tubule is a low blood hydrostatic pressure inside the peritubule capillary, an extremely high colloid osmotic pressure inside the peritubule capillary, with a high tubule hydrostatic pressure inside the proximal convoluted tubule. And that drives reabsorption. That drives the movement of water from the proximal convoluted tubule into the peritubule capillary. And in the proximal convoluted capillaries, we have something that is referred to, and within the proximal convoluted tubules, we have transport proteins, right, that have a limit to what they can actually transport. So the rate at which we go ahead and we move through transcellular transportation, those molecules from the cuboidal cells into the peritubule capillaries is based on the number of transporters or receptors that we have. And we refer to that as the transport maximum, right, or the TM, the maximum rate at which you can reabsorb solutes that are within the tubule. And each solute has its own number. All right, each solute has its own TM, right, or transport maximum. Glucose is probably the most important one because all of glucose gets reabsorbed within the proximal convoluted tubule. And so the TM, the transport maximum for glucose, is 320 milligrams per minute of glucose. Even after a heavy meal, we are reabsorbing glucose right around about 125 milligrams per minute of glucose. So we don't even come close to the glucose maximum, the transport maximum for glucose. In individuals who are diabetic, what happens is that glucose is not being reabsorbed inside of the cells, inside of the tissues for the use of cellular respiration. And so that glucose is all getting excreted into the filtrate. And at that point in time, you do exceed the TM. You do exceed the transport maximum for glucose. And so not all of that glucose can be absorbed because the body's not sufficiently using it. And so when that happens, you have glucose that's left in the urine. And that is why when you do a chem stick test, right, or the p-test, and you stick the dipstick into the urine sample and it comes up positive for urine or for glucose, this is why. Because you've exceeded the TM within the proximal convoluted tubule. Back in the day, back in the 1600s, physicians would actually diagnose diabetes by taking a urine sample, handing it off to the intern, and saying, "Taste this." And if the urine was sweet, it indicated that the glucose was still in the urine and wasn't being reabsorbed, and they would actually diagnose those individuals, usually with diabetes. All right. Okay, so now, that was all proximal convoluted tubule. Aren't you glad we're doing this? All right. Let's take a few minutes to talk about what is happening in the loop of Henle, because in the loop of Henle we see the other 24% or so of water being reabsorbed. Remember, about 75% of the water is being reabsorbed in the proximal convoluted tubule, and the remainder of that water, all of the remainder of that water, is going to be reabsorbed in the loop of Henle. And so how this happens is through using what we call the countercurrent multiplier mechanism, right? Or the countercurrent mechanism. Countercurrent multiplier, and I'll define that a little bit more for you here in a little bit. And so we can go ahead and we can increase the water reabsorption in the loop of Henle through this mechanism that we're going to spend some time talking about. The other way that we can go ahead and regulate the reabsorption of water is within the distal convoluted tubule, and that's done through antidiuretic hormone, and we'll talk about that next. But the countercurrent mechanism creates and maintains an osmotic flow by basically swapping salt for water. And this is where the medulla of the kidneys, the renal pyramids, become such a vital role. And this is why that loop of Henle dips down into the medulla. So let's go ahead and jump into this. By the way, let me just define real quick here for you. All right, MOSM, which is a milli osmol. Right, a milliosmol, and this is simply the number of moles of a solute that contributes to the osmotic pressure of a solution. All right, so the milliosmol is the number of moles of a solute that contributes to the osmotic pressure of a solution. As you increase osmotic pressure, you can increase the rate of water reabsorption. And as you decrease osmotic pressure, you decrease the rate of water reabsorption. And so when you talk about balancing the solute concentrations, we can do that through the regulation of water. And that's exactly what the counter current multiplier mechanism does. And what we see here is we see basically a two-step process. Sodium chloride is actively reabsorbed into the interstitial fluid. Now that interstitial fluid is the renal pyramid. Right, or the medulla. All right, so what we're doing is we're super concentrating with salt the renal pyramids. And in doing that, you create a hypertonic environment that the water in the filtrate coming down into that loop of Henle is then forced to move into the interstitial fluid. And then, as it dilutes the salt, that water then moves back into the vasa recta, which again is the capillaries that are surrounding that loop of Henle. So we remove salt actually on the ascending loop, or the ascending branch of the loop of Henle. It super concentrates the medulla of the renal pyramid, which draws the water out of the filtrate coming through the loop of Henle. That decreases the solute concentration within the medulla and then allows the water to be moved into the vasa recta. And so we therefore reabsorb that water. And it kind of looks like this. All right, so step one. All right, here's step one. This is the ascending branch right here. All right. The salt, the sodium chloride, has a higher concentration here in the ascending loop than in the surrounding renal pyramid. And so that salt is moved from this area of low concentration, from this area of high concentration to this area of low concentration. That salt just moves, and as it does that, it super concentrates the renal pyramid. And as it super concentrates this renal pyramid, it drives the water out of the filtrate coming down the descending loop and down into this loop of Henle. And so then that water is then reabsorbed, and then you have your peritubular capillaries that are right here. This is the countercurrent part of it, because your filtrate get a load of this. Haha. This is why I love this stuff. Hold on one second. Your filtrate is moving in this direction. Your filtrate is moving in this direction, but your peritubule capillaries, your vasa recta is moving in this direction. So it's countercurrent. It's countercurrent. And it's a multiplier because you're super concentrating the sodium on the descending branch from removing it from the ascending branch. And so you're pulling that much more water out of the descending limb where the loop is here. And you can also see that you actually constrict. Your diameter of the loop decreases, and so this thinner loop that's actually made of simple squamous for easy diffusion of water. All right, easy diffusion of water because remember you have simple squamous epithelium. All right, allows for diffusion of water. And so that water just comes right on out. The vasa recta, again, moving in the opposite direction of the filtrate, is there to go ahead and just reabsorb that water. Right. And so that's what you're seeing on this slide right here. Now you're seeing the addition of the vasa recta right here. Let me just come over here. And so your vasa recta is moving in this direction. Here's your proximal convoluted tubule down into the descending branch, down into the loop, which is made up of simple squamous, and then up here. And so watch what happens. You concentrate the little balls that you see there are salt. All right, so this is the salt. And so you're super concentrating the osmolarity of the salt. And then as it comes up into this ascending loop, it just goes ahead and just explodes outward. All right. And as you're doing that, that salt is then being, again, reabsorbed, and it's going into the interstitial here, which is going to draw water out. But it's also being sucked up and brought into the vasa recta over here. And so you go from, in the vasa recta, 300 millimoles of salt, 600 because now it's starting to be drawn from the ascending loop, 900, 1200 millimoles of sodium chloride in the vasa recta. All right. At the same time, you're super concentrating here in the interstitial as well, which is now drawing that water out, and that water is now being reabsorbed into the vasa recta up here. All right, and so you're super concentrating this whole area, which is forcing water this way, and on this side, you have a little bit of water that's moving out, not much, you're not losing much, but you've got a lot of sodium that's coming in and being reabsorbed on this side. So it's a fascinating dichotomy that happens with this countercurrent multiplier. You're just it's efficient, and it's really simplistic and ingenious in how we use the molarity to go ahead and drive the osmosis. And so there's again a short video that is on that. All right, secretion. Spend a few minutes talking about that. I promise we're not going to belabor this too much. But tubular secretion happens in reverse. So we're going from the capillary back into the filtrate. And so that's just in case we have excess waste that has now been removed and reabsorbed, and we need to balance it out a little bit more. And so what are some of the things that might be included in that? Urea and uric acid that we would have accidentally reabsorbed through solvent drag. In the proximal convoluted tubule, you might have some more ammonia in there, catecholamines, epinephrine, norepinephrine, and dopamine, right? Prostaglandins, which are inflammatory hormones, creatinine once again. You might have more acid-base balance that needs to go on within the blood, and so you might be secreting hydrogen ions if the blood is too acidic, or you might be secreting bicarbonate ions if the blood is too basic. And so you have all of that that's happening within, again, this is primarily within the distal convoluted tubule. The other thing that will be secreted in the distal convoluted tubule are drugs. And so any kind of medication that you may be taking, even if it's Tylenol or aspirin, the metabolites of those will be go ahead and will be gotten rid of within the distal convoluted tubule and added to the filtrate. We define this as renal clearance. Every drug has a renal clearance, or a rate by which the drug will be filtered out using the kidneys. And this is why sometimes drugs have to be taken, or medications have to be taken 3 or 4 times a day, because of that rate of renal clearance. And so within the distal convoluted tubule, hormone regulation, again, aldosterone, which we've already talked about, helps in salt reabsorption, right, or retaining. So it's a salt retaining hormone, so we're going to go ahead and we're going to keep that salt, again, secrete it back into, I'm sorry, try that again. Aldosterone is salt retaining, and so that's going to reabsorb it from the filtrate back into the vasa recta. And again, that typically happens in the distal convoluted tubule. And we know that that happens in response to a drop in pH, right? Because that's going to drive water reabsorption once we get into the collecting duct. Atrial natriuretic peptides is a hormone that's secreted from within the heart, and that causes the excretion of excess salt. All right, so if you have too much salt in the blood, you'll go ahead and you'll get rid of that, and so that's a secretion hormone. ADH, we already know, antidiuretic hormone, when it is secreted, reduces, or I should say, it reduces the amount of urine that is produced. All right, so it causes for water reabsorption. If we inhibit ADH, then we go ahead and we can actually increase the rate of urine production. And parathyroid hormone also has some regulatory effects here in the distal convoluted tubule. Again, here's another little video here for you to go ahead and kind of review reabsorption and secretion within the distal convoluted tubule. You got a pretty little diagram here for you that kind of summarizes for you where reabsorption and secretion is happening and what exactly is moving and where. And then the collecting duct. And really it is the lower end of the collecting duct that is actually in the renal pyramid where we're going to go ahead and see water reabsorption occur. And again, this here just kind of summarizes everything for us a little bit more on these 2 slides here, and you have those slides in the PowerPoint. And so that brings us to the end of the urinary system. And so I encourage you to go back and review this, jot down questions that you may have. We can bring them into our class time, and feel free to ask questions, all right, for clarification. And so with that, happy studying, happy reviewing, happy thinking, and I will see you guys on the flip side.